It's my pleasure to introduce you our speaker today, Dr. Carter, who was my postdoc advisor several years ago. Dr. Carter is a distinguished research chemist at the Air Pollution Research Center at the University of California, Riverside. He's the winner of the 2005 ARB's Hawkins-Smith Science Award. Also, he's the 2005 Best Paper winner of the Journal of Atmospheric Environment. Over the past 30 years, he has dedicated himself to study the photochemical mechanism of VOCs and the nitrogen oxides, leading to the formation of ozone. Dr. Carter is a world leader in developing these chemical mechanisms and the ozone-forming potential of VOCs. His findings on photochemical mechanisms have long been incorporated as an essential element in most urban and regional airshed models. Reactivity scales devised by him have enabled air pollution control agencies to focus their regulatory efforts on VOC with high ozone-forming potential. Since his first mechanism, SAPRC-90, Dr. Carter has progressively updated the mechanism and leading successfully to the SAPRC 1991, SAPRC 1997, and the SAPRC 1999 mechanisms. Today, I'm presenting you the SAPRC-07 mechanism. Please help me welcome Dr. Carter.
Thank you, Dongmin. I'll okay, is it on? As I'll be discussing the recently completed project we'd had with the ARB to develop an updated SAPRC chemical mechanism. And this is a brief outline of the presentation. First, I'll give an overview of the SAPRC mechanisms and the approach and their structure, just to put a background, and then I'll discuss the updates that were done for what I call the SAPRC-07 mechanism, and then very briefly show possible changes in ambient ozone predictions that might happen when you go from SAPRC-99 to SAPRC-07, although this needs to be looked at in actual Airshed model calculations. And then discuss some of the changes in the ozone reactivity, particularly the MIR values that result with the MIR scale updated, and give list some of the work that wasn't quite completed for this project that needs to be done in the near term, and some of the longer term recommended research. Well, in general, the chemical mechanisms, the gas-based chemical mechanisms, have two main uses in airshed models. First is just to represent the chemistry and formation of secondary pollutants from the emitted VOCs and NOx, so that you would use that to predict the effective control strategies in various scenarios. Different kind of mechanisms to do that, but another requirement for this particular mechanism is to predict ozone reactivity scales for different chemical compounds, VOCs, that is the change in ozone per change in VOC for regulatory applications, like the MIR scale that's used in California. And the requirements for this is that the chemical mechanism should represent the current state of the science in atmospheric chemistry, and but the current state of the science is not such that you can predict a priori what all of the reactions and everything is, and there's a lot of uncertainties, and you need to sort of give the mechanism a reality check. And the way that the only real way to do that, as far as isolating just the chemical uncertainties, is to test it against environmental chamber experiments. So it needs to give predictions which are consistent with environmental chamber results. And then for its use in reactivity scales, it's got to be able to appropriately represent the many hundreds of types of VOCs that are relevant to reactivity scale calculations or regulatory applications that use reactivity. But also for Airshed models, it has to be able to represent complex mixtures of compounds in real airsheds in a computationally efficient manner. So these are sort of the requirements. Now, the SAPRC mechanisms are somewhat different than the condensed mechanisms in that the condensed mechanism basically is one complete unit that represents the VOCs and the NOx, but because the SAPRC mechanism is intended for the two purpose of being used in an airshed model, but also for reactivity calculations, it's broken up into different components. The base mechanism is the reactions of the organics and the common organic products that are present regardless of what you're using it for. For the reactivity scale calculations, you need the mechanisms for the individual VOCs, of which there are many hundreds that are represented. In the SAPRC-09 and also the updated version, it's relied heavily on a mechanism generation system to derive explicit mechanisms for the compounds that are condensed using lumping rules, and I'll summarize that in the next few slides. But you can't use that for all of the types of compounds. For other compounds like aromatics, you don't really know how to estimate them that well enough, and so you have to use estimated or parameterized mechanisms. So starting from that, the base mechanism and the mechanism for individual VOCs, if you put it all together, you get something like the European master mechanism with hundreds of species and thousands of reactions, which is the software we use now is not particularly efficient for airshed models. So what to do is derive a condensed mechanism from the detailed mechanism that can be used in airshed models by using a limited number of lump model species whose reactions, rates, and parameters are derived from those of the compounds they represent. And so this mechanism depends on the composition or mixture that's taken as representative of the VOC emissions from all sources. Now, just briefly discuss the mechanism generation system, because this is an important part of the reactivity scale calculation. Now, this is basically a computer program and a set of chemical assumptions and chemical estimation methods for generating reactions of a variety of different compounds. First for their initial reactions with OH, et cetera, and then for the subsequent reactions of the various radicals they form. And the measured rate constants are used, or rate constant ratios in the case of radical reactions, if you have that information. Otherwise, you have to use various estimation methods. The estimation methods include structure reactivity estimates for initial reactions like OH and ozone, et cetera. And then for the peroxy radical reactions, one of the important parameters is the nitrate yields in the RO2 plus NO reactions, which depends on the size of the radical and substituents. Then there's one of the most complicated parts of the atmospheric chemistry of VOCs is the many types of ways that alkoxy radicals can react. And so you have to use various estimation methods for those. And in some cases, they can be extrapolated from known reactions. In some cases, they have to be adjusted to fit chamber data. In other cases, you just have to guess. I won't go into the detail here. The generated mechanisms, when you can become quite large for molecules of of reasonable size. These are the numbers of reactions that it generates just from the primary reactions. This is not considering the reactions of the products, and you can get into thousands of reactions and many hundreds of products for some of the larger molecules. Even for the aromatics, just looking at the primary reactions, you can estimate a fair number of reactions and products. So that's why you sort of need a computer program to try to keep all that together, and then use the lumping rules to get that into the mechanism. Well, the mechanism generation system is used in SAPRC-99, has a number of limitations, which is also, in some cases, they're still true. They only generate mechanisms for systems, the reactions in the presence of NOx, those are the reactions that are important for ozone formation. But in the absence of NOx, you have peroxy radical reactions, and it doesn't generate those. So the models just use them in an approximate way. The limitations of thermochemical group estimation data limit the types of alkoxy radicals for which estimates can be made. Estimates are uncertain for photolysis reactions. Unsaturated radicals, such as radicals with both double bonds and radical centers can undergo a wide variety of reactions for which estimation methods are unknown or very uncertain. And these include radicals formed from aromatics, but also from diolphins such as isoprene. The system still doesn't take steric effects into account, which can be important for certain systems. And the system used for the SAPRC-99 mechanism couldn't process compounds with more than one double bound or more than one ring, although the updated mechanism now can handle that. Well, this is the status of the SAPRC mechanisms is summarized here. The current version that's been used, as Dongmin indicated, for a number of years is the SAPRC-99, which represents the state of the art as of 99, as you might imagine. It's been used to calculate the reactivity scales that the ARB is currently using. The scales were updated in 2002, but the mechanism itself, the base mechanism, and most of the VOC mechanisms were changed. Some VOC mechanisms were updated, but it's still basically the SAPRC-99 mechanism. And many of the current Airshed models use the fixed parameter version of SAPRC-99 with the condensed model species. These were derived based on the mixture of actually ambient measured VOCs that are used in the base mixture representing emissions in the reactivity scale calculation. Okay, and so this mechanism was more than almost 20 years out of date. The ARB wanted to get it updated, so we had a project to develop an updated version of it. Of course, if it had been on time, it probably would have been the SAPRC-04 mechanism, but it actually was the SAPRC-07, because that's now when it was completed, and it's finally been completed, and the screening committee has approved the report, but I still have to submit the final report, which has a few minor changes. The development, evaluation, and documentation, therefore, is completed, but there's still work needs to be done on implementing it. It hasn't actually been implemented in the Airshed model, any grid model to my knowledge. All right, so the major objectives of this summarizes the major objectives of this mechanism update project. The first was to update the rate constant and the reactions that it incorporates in the base mechanism, and also the estimates to the current state of the science. The other one that the ARB wanted, at least as an optional feature, was to add chlorine chemistry with updated rate constants, et cetera, for that. And then one of the big problems with it was obvious with the SAPRC-99 mechanism that there were problems with the aromatics mechanism. It was oversimplified and didn't simulate adequately all of the data. So to improve the aromatics mechanism was one of the objectives. And there was a lot of new data on aromatics that could be used for that. And then the other objective was to update and enhance the mechanism generation system, to update the estimation methods and enhance its capabilities, at least to support mechanisms for chlorine atom reactions, but hopefully also to help in generating mechanisms for aromatics. And then now the first objective was, two objectives were basically essentially successfully completed. The third was partially completed, but it could have been better. And the same thing for the mechanism generation update. Improved capability will be adapted to secondary PM models. It has been improved that way, but it's not really a secondary PM mechanism. More work is needed to complete that process. Another objective was to represent additional types of VOCs of interest to the ARB, and we did add quite a few VOCs, but not all of them that they're interested in. And then a final objective that we had in the proposal was to develop new condensed mechanisms based on this detailed version, perhaps including one that's comparable in size to carbon bond 4. Unfortunately, because of time, I ran out of time before I could do that. Okay, so now I'll go through the mechanism updates briefly. Oh, incidentally, if any of you have any questions or something's not clear, you can feel free to interrupt me. As far as the base mechanisms, The inorganic and organic product mechanisms were updated based on recent evaluations, and we added the inorganic chlorine reactions and also representative chlorine substituted product species, and updated those rate constants as well. So that now this update resulted in changes in small changes in most of the rate constants. Few of them weren't changed, but some of them changed quite a bit. Some of them were not that important, but some of them were, and potentially the most important, potentially significant changes are listed here. Perhaps the most important might be the increase in the OH plus NO2 rate constant, which I sort of consider the second most important reaction in smog. It's the main termination reaction for OH and also removing NOx. And this increase is based on the new NASA evaluation, and incidentally, it's the same rate constant that the carbon bond 05 mechanism uses, and that will tend to make the mechanism somewhat less reactive, and you see the impacts of that. That's probably due to that later on. One of the reasons that the SAPRC-99 mechanism is more reactive than carbon bond 4 is because of the difference in this rate constant. Other changes which may have the peroxy plus HO2 rate constant went down by quite a bit. I don't know how important that is, but it sort of will affect the transition between the region where you're forming ozone and when the peroxy plus peroxy reactions are occurring, although I'm not sure how important it is, but it did change by a fair amount. There was a slight increase in the NO2 photolysis rate. That actually won't affect the simulations of the chamber experiments, because when you're modeling chamber experiments, you put the NO2 photolysis rate to the measured value, so it won't change that, although it changes all the other photolysis rates. But it will result in somewhat faster photolysis rates in all the ambient simulations, and therefore maybe to some extent offset the increase in the OH plus NO2 rate constant. And then some other photolysis rates changed by a fair amount too. But the importance of those, we really haven't done a systematic study of what these changes, how important these changes are, and it's probably something that needs to be done. The mechanism generation system had some updates as well. All of the rate constants that's incorporated in the primary reactions were updated based on some of the current evaluations. Well, some of them didn't have to be changed, but I looked at the evaluations for them, and they were updated or added in some cases when there's new measurement data. The capability of generating chlorine plus VOC reactions were added using structure reactivity methods to estimate chlorine plus VOC rate constants. And then for the chlorine plus saturated compounds, they could be generated using the same procedures as for the OH system because they're forming the same radicals. The only difference is they're formed in a little different yields relative to each other. So that part was easy. For alkenes, you also form radicals that have chlorines on them, and you end up getting alkoxy radicals that you don't have thermochemical group estimates for, and so you can't generate mechanisms without having to make explicit estimates for individual reactions. So that was sort of limited. So what I had to do with the olefin reactions is chlorine plus olefin reactions is just to use some representative ones to represent the others. It's probably not that important in ambient simulations because most of the chlorine will react with the alkanes rather than the olefins because there's so much more of them and they react very fast. The capability to represent compounds with more than one radical, with compounds and radicals with more than one ring and more than one double bond was added, and that allowed you to, first you could generate then mechanisms with terpenes because they have more than one ring, and it was used as an aid in the development of explicit mechanisms for aromatics, but we didn't end up actually using an explicit mechanism for aromatics, but it turned out to be a tool for developing the mechanism that's used, which I'll go into in a minute. And the methods were developed to generate initial reactions, generate reactions of some of the unsaturated carbonyl ring opening products, which was used in the basis for the aromatic or aromatic product mechanism, although we still had to use a bunch of simplified assumptions for photolysis, which really couldn't be estimated. Now, for the aromatic mechanisms, that's an important uncertainty in all of the in atmospheric chemistry because even though there's been a lot of data studying them, every study just indicates that it's messier than the last one. But the SAPRC-99 mechanism used a sort of a parameterized mechanism adjusted to fit chamber data, and it used sort of parameterized species to represent some of the uncharacterized ring opening products. And it didn't perform that badly, but it did give poor fits to some chamber experiments. It gave poor fits to the effects of adding CO to aromatic NOx experiments, and also gave poor fits to measurements of direct reactivity, which I'll show you in a minute. So the approach, so it was clear that the mechanism ideally should be updated, and there's Calvert and Atkinson and co-workers had done a fairly comprehensive book several years ago, giving a lot of new information about aromatic systems, which hasn't been incorporated and needed to be. And so the approach that we had intended to use in updating the mechanism was to try to derive explicit or at least semi-explicit mechanisms for the ring opening reactions of the aromatics and the reactions of the unsaturated dicarbonyl ring opening products based in the data in the current evaluation, and then derive somewhat more condensed mechanisms for Airshed models based on these explicit mechanisms. So then instead of the approach that was used in SAPRC-99 or carbon bond and practically every other mechanism is just using model species that you don't really know for sure what they represent. The model species now are based on at least some concept of particular real compounds, although we still had to adjust photoreactive products. Actually, what was adjusted was overall quantum yields to fit the chamber data. Okay, now this shows the assumption that the mechanism incorporates as far as the aromatic ring opening reactions, and it's almost certainly an oversimplification of the real world, but we know that based on the information, you get a whole bunch of products. It's sort of hard to figure out where they come from. Some of them are probably not primary products anyway, and some of them are things formed in the analysis system. But based on thinking about it, this is the sort of structure that we're assuming for the ring opening products. So what I'm showing here in this example is for benzene plus OH, and then showing only the ring opening process, not showing the process forming the ring retaining products. Anyway, the OH will add to the aromatic ring, forming this unsaturated radical, and that will add to O2, forming the aromatic OH adduct. This is one of the two possible radicals that could be formed in the benzene system. And now what we assume now, and basically what the existing mechanisms assume as far as what we know about them, is that they form alpha dicarbonyls and like glyoxal, and a variety of unsaturated carbonyl products that are not as well characterized. But the way we'd explain the formation of the alpha dicarbonyls is basically the O2 adds internally to the ring to form a bicyclic structure that sort of rearranges and eventually decomposes to form the alpha dicarbonyl and then the co-product, the 1,4-dicarbonyl. But that can't be the only thing that's occurring, because seeing these other products and also the yields of the alpha dicarbonyls is not enough to count for all the reaction, even if you take into account the ring retaining products. So what we're assuming now is that the competing reaction is that this radical can also undergo another unimolecular reaction, but basically the hydrogen moving over from the OH to the oxygen in a six-member ring transition state, essentially regenerating OH and a 1,6 unsaturated diunsaturated carbonyl. The important thing about this is that this competition is a competition between two unimolecular processes, and so it doesn't depend on what reactants are present. And you sort of need to have that assumption in order to fit the fact that the product data don't indicate a very strong dependence on conditions for the yields of these products. So you sort of have to have a competition for that. The other thing is the direct reactivity data indicate you can get better performance if the model has fewer NO to NO2 conversions as far as the reaction is concerned. And so this particular reaction, which may or may not be realistic and some theoreticians don't particularly like, it has the advantage of not depending on the NOx, and also it generates OH without NO to NO2 conversions, which actually helps you. The alternative process is starting with the again the OH-O2 adduct, and then as having the unimolecular reaction, as I showed before, you're forming the alpha dicarbonyl, etc. But competing with this, instead of undergoing a unimolecular reaction, reacting with NO to form essentially the same product as before, but after NO to NO2 conversions. And this is sort of the mechanism in effect that was assumed by SAPRC-99, because it has the NO to NO2 conversions regardless of what ring opening products it is. But what it doesn't account for is the fact that this competition is actually dependent on the NOx levels, which SAPRC-99 doesn't represent, and also which doesn't seem to be consistent with the product data. So what we then basically ended up doing for the ring mechanism is, for a particular aromatic, is to use the measured yields of the alpha dicarbonyl products, which have been measured, like glycol, methyl glycol, and whatnot. Those yields are known for benzene, toluene, and the xylenes and trimethyl-benzenes. And then you assume that the 1,4-dicarbonyl coproducts yields correspond to the yields of the alpha dicarbonyls that are measured, and you have to actually look at all the detailed reactions as far as which one is the coproduct for it, and the mechanism generation system was useful for that. And then for the remaining process, which is non-alpha dicarbonyl ring opening process, you assume it forms products like these, and the mechanism generation system was used to derive sort of the different types of products that different types of isomers. In the case, there's only one in the case of benzene, but if there are alkylbenzenes, you get different isomers. Okay, so for the, of course, so that sort of takes care of how the initial reactions were represented, but probably more important is how you represent the products, because they're what accounts for the reactivities of the aromatics. So what we did, the SAPRC-99 used parameterized mechanisms for phenols and cresols, and they didn't really have time to go look into that in detail, so they were unchanged. In fact, Ian Barnes in Germany and some of his colleagues in Europe have product data on the reactions of phenols and cresols that indicate that quite a different type of a mechanism that we use, but I couldn't get that to be consistent with the chamber data, so I finally had to sort of give up because I was running against the clock there. But one of the things that Ian Barnes did find, which I think might be interesting to the modelers, is if you have nitro cresols, which are formed in the NO3 plus cresol reactions, they photolize to some extent, not a huge extent, but a non-negligible extent, to form HONO. So what you have here is another process to form HONO in the atmosphere that the models are not predicting. And some of the things, and this was discussed at the atmospheric chemistry conferences, there have been measurements of HONO in the atmosphere at higher levels than can be accounted for, and maybe some of it is coming from the aromatics. I don't know how significant that is, but anyway, that's in the SAPRC-07 mechanism, and so you, oops, I didn't want to do that. So you can look at that. The mechanisms for the alpha dicarbonyl products were updated based on the evaluations. The mechanisms for the model species representing the unsaturated dicarbonyls, instead of being used totally parameterized, were derived based on the estimated mechanisms for the actual compounds that predicted to form from the alkyl benzenes. Now, for the 1,4-dialdehydes and aldehyde ketones, the data in the Calvert reviews suggest that they photolized rapidly, and they actually gave action spectra for them, or at least absorption cross-sections for them. And there's also information on photolysis rates in the U4 chamber from which you can derive at least overall quantum yields. And so we, in effect, have overall photolysis rates for these products. But in order to simulate the data, they must form a fair amount of radicals. But if you have them all forming 100% radicals, you get too much reactivity. So what they ended up basically having to do is adjust the overall quantum yield for the products for each compound based on the data. But the approach that we used was, rather than have a separate compound for each particular aromatic, which there's quite a number of aromatics for which we can adjust mechanisms. I ended up using 2 model species to represent these. One of them that photolyzes to form radicals, and one of them that photolyzes to form stable compounds, but otherwise reacts just the same way. So therefore, the sum of those 2 is then equal to the total alpha dicarbonyl yield, and then the ratio of those 2 is basically what's adjusted to get effectively an overall quantum yield. So this allows you to use 2 model species to do the job of a number of them. And the relative yields of those are adjusted on the chamber simulations. Now for the di-unsaturated 1,6-dicarbonyls that are formed in the other reaction, there are limited data indicate that they don't photolize as rapidly, and also 1,4-diketones that you form from like paracresol and whatnot, not paracresol, paraxylene, they don't photolize as rapidly either, at least don't photolize to form radicals. And so they were lumped into a separate model species that's assumed not to photolize, although they're still reactive model species. They react with OH pretty rapidly and ozone and NO3, and that's in there. Now, I mentioned direct reactivity. Direct reactivity is the number of NO to NO2 conversions that occur in the reactions of a VOC. It's not the only factor that affects its reactivity, but it's one aspect of the mechanism. And for a previous ARB program, we developed a HONO plus VOC flow system that gives a measurement sensitive to direct reactivity. So I won't go into detail about that, but we found that the SAPRC-99 mechanism's predictions of direct reactivity were reasonably consistent with the data for most compounds, but for aromatics, and this shows the results here where the black is experimental and the yellow is the SAPRC-99. For the aromatics, the direct reactivities that the model calculated was considerably higher than the experimental value, which suggesting that there's fewer NO to NO2 conversions in the actual reaction than the model had. Now the SAPRC aromatic mechanisms has fewer NO to NO2 conversions because of that other reaction forming OH directly, and that in fact gives a prediction of direct reactivity which is somewhat more consistent with the data, but still it's still somewhat high. So it partially fixed that problem, but not completely. Another problem that was partially fixed, but not completely, was the fact that the mechanism underpredicts the SAPRC-99 mechanism, which is adjusted so that it will simulate aromatic NOx experiments. If you add CO to the experiment, you would think that the model predicts that the ozone would be enhanced because of the radicals formed from the aromatics. But what we see experimentally is that the ozone is enhanced by about twice as much as what the model predicts. And the blacks, and here are the white squares is experimental with aromatic by itself. The diamonds is aromatic with added CO. The black lines is the SAPRC-99 predictions for the 2 experiments. And you see it's about, and this is the effect of adding the CO, and it underpredicts it by a fair amount. Now the SAPRC-07 mechanism, it still underpredicts it, but it doesn't underpredict it as much. So this is another case where it's sort of better, but still not good enough. Okay, now for other mechanism update, it wasn't an update as much as just changing the structure of the mechanism so it could be adaptable to PM models better. One of the problems with chemical mechanisms in general is the proxy, you have to have a lot of different peroxy radicals involved because of the different types of VOCs. Their first reaction is to form peroxy radicals. In the presence of NOx, the peroxy radicals mostly react with NO, and that's the only important reaction that's really important to affect ozone. But when the NOx gets lower, the peroxy radicals end up reacting with themselves or other peroxy radicals, and those reactions will affect other products besides ozone, including perhaps PM formation. But because of the many cross reactions, you can't really represent them explicitly, and you have to use various assumptions or chemical operator methods in order to do it. And because of the approach that was used in SAPRC-99, and it's also used in other condensed mechanisms like the the carbon bond mechanism, is basically to, I won't go into the details of the operators, but in effect what they do is you use some particular model species to represent the effects of the peroxy radicals on NOx and other radicals, but then you assume that the products formed are the same regardless of how the peroxy radicals form. And that's okay as far as predicting ozone, but the assumption that in the real world the nature of the organic products change depending on whether the peroxy radicals react with NO or HO2 or other radicals. And for ozone maybe that's not so important, but what we're finding as far as people who are trying to model secondary organic aerosol formation is that the hydroperoxides formed in the HO2 reactions and also organic nitrates are important precursors to SOA. And if you have a representation that doesn't allow you to change the hydroperoxides, then you have a problem with predicting SOA. So in order to address that, even though the SAPRC-07 mechanism in its present form does not really have everything needed for doing SOA formation, it'll provide a structure to do it by changing the representation of the peroxy radicals to permit the use of separate model species for hydroperoxides and organic nitrates. And for example, there's data indicating that the yields of secondary organic aerosol from aromatic reactions have a much stronger dependence on NOx conditions than can be explained by the current models. But if you assume that the aromatic hydroperoxides are important PM precursors, then you can explain that difference. And so in order to allow for that, the model uses a separate hydroperoxide species that are formed from aromatics. There's some of the next slides go into some of the details of that, which I'll skip, but it's in your handout. If you have any questions about that, you can interrupt me at this point. But you'll be quizzed on it later, though. Anyway, another important update that's probably more of immediate interest to the ARB is the mechanisms for many types of VOCs that are used for the reactivity calculations have been added or improved. There's a significant, about a 20% increase in the number of VOCs that have distinct estimated mechanisms. And these included individual alkenes, and in some cases oxygenates in emission inventories that were not previously weren't previously represented, but that I found them in emission inventories. And the nice thing about the mechanism generation system is basically all you have to do is feed in the structure of the thing, and it'll come out with a mechanism. It may not be right, but at least it's something that you have. And the system actually doesn't perform that badly for some of the simpler compounds and some of the oxygenates. And in the case of the aromatics, it derives some separate estimated mechanisms for the higher alkyl-benzenes that I think should be a little less approximate, perhaps. The SAPRC-99 used lump molecule representations, which basically represented all the aromatics based on mechanisms for alkyl benzene, for methylbenzenes. Well, if you have an ethylbenzene or a propylbenzene or something like that, you actually have more reaction off of the aromatic ring because there's more stuff there to react, and you get actually different lower reactivity products that way compared to reaction on the methyl group, and you also get different types of products. And so taking that into account for the higher alkyl-benzenes perhaps derives a somewhat better way of handling complex aromatic systems, although how much, and I think that would be better for reactivity calculations. How it would affect Airshed calculations, probably not that much. But another important improvement was the estimates for halogenated compounds, because now it has chlorine chemistry, and also as a result of the project that they had for pesticides, which included some chlorine-containing olefins, we found that the chlorine-containing aldehydes that they formed are a lot more reactive than the aldehydes that are formed in not chlorine-containing systems, or like propanaldehyde and whatnot. And the model previously used propanaldehyde to represent all of those. Well, that basically doesn't work because those halogenated aldehydes photolize a lot more rapidly, and you have to put that in the model in order to predict their reactivity. So therefore, for these chlorine-containing compounds, we use these halogenated, we add model species for these halogenated aldehydes to handle that, and the result, which I'll show you in a minute, will be higher MIRs for some chlorine-containing compounds than we had before. Now, the other big part of the project is since you've completely updated the mechanism and changed it and everything and all the rate constants, you have to reevaluate it against the chamber data. And so this is the database, the large database used for the SAPRC-99 evaluation, but also newer experiments we did in the chamber and the TVA environmental chamber database that we set up for modeling as part of the low NOx project several years ago, and a few older UNC experiments, but those are not very good and probably should be done with a better data set. But so the primary was the various UCR and TVA chambers was the main database that was used. As far as the runs, there's a very large number of runs, different types of characterization, single VOC runs, incremental reactivity experiments. That's experiments where you look at the effect of adding the particular chemical onto a base case simulation representing ambient conditions, which is really the only way you can evaluate mechanisms for some types of compounds, and various mixtures, and a very large number of VOCs also for which you have chamber data, mostly for the purpose, a lot of them for the purpose of improving their reactivity estimates. And as I'll show you in a minute, the performance in simulating the database was comparable to SAPRC-99. It really wasn't all that much better. It was better in some cases, particularly perhaps for some of the individual aromatics, but in some cases it wasn't quite as good. So, I mean, you think when you update things should be better, but of course when you find when you update software, things are usually worse too. So anyway, for the single, this sort of gives an overall sort of average and distribution of the model errors for all of the single VOC experiments like propene NOx, toluene NOx, etc. This first plot shows the model error for predicting ozone formed. It didn't say that. This is ozone formed plus NO oxidized, which is a measure of ozone formation, for each hour in the experiment up to 6 hours. And generally the first hour is more difficult to model because that's more sensitive to conditions and chamber effects, but generally there's very little bias for both the SAPRC-99 and SAPRC-07 mechanism for these single experiments after the first hour. And this is the distribution here. Most of the runs were within the sort of the plus or minus 30% range. Some examples is to say for different types of experiments is the propene. Again, this is the model error versus the radiation time for various types of propene experiments done in different chambers. The UNC chamber, the data didn't perform, model didn't perform very well for UNC chamber. I don't think it's probably well characterized, but for the others, it's reasonably good. But you see there's somewhat different performance for SAPRC-07 and SAPRC-99, and in some cases the performance isn't quite as good for SAPRC-07. In some cases it's better. For propene, for xylene, a similar type of thing. There's SAPRC-99, the very types of experiments actually fit reasonably well. And for SAPRC-07, they did two. Then the added CO experiments, there was more of a discrepancy for SAPRC-99 and SAPRC-07, which I had mentioned before. But for the TVA experiments, it was slightly different. Now, an interesting result that's just a little bit of a sort of surprising and a little bit of concern, if you consider all of the mixture experiments, complex mixture and sometimes just simple mixture of a few compounds, the model error for SAPRC-07 was actually slightly worse than SAPRC-99 on the average. If you're looking at the model error as a function of irradiation time, SAPRC-99 was relatively unbiased, except maybe after the first hour. You're not talking about large errors now. It's 10 or 20% isn't large for chamber experiments. But overall, there was a definite positive bias in the SAPRC-07 that may or may not be statistically significant. You see here the distributions, and you see that significance may not be that obvious, but it is somewhat slightly better for the older mechanism. If you're looking at the different types of mixture experiments, that was sort of interesting too, is that you got some types of mixtures where the SAPRC-07 had more of a tendency to underpredict than it did before, and for other experiments that had more of a tendency to overpredict than it did before. So it seemed to depend on the type of experiment. And with mixture experiments, you don't really know what the cause of things are. You just run it and you see what the answer is. But it would take sort of to try to understand what's to the bottom of it would require a fair amount of work. But I think it might be indicative about, maybe it's because the biggest change might be the OH plus NO2 rate constant, because changing that rate constant, when you go to evaluate the mechanism, you find you have to change a lot of other things to get the data to fit as well. Like you have to redo all the characterization runs, which changes the radical source for all the experiments that you're modeling. Turned out that the radical yields and ozone olefin and some of the other reactions that fit the chamber data have changed when you change the mechanism. So you're changing a lot of things, and the effects of all these different changes are not obvious. But if the OH plus NO2 rate constant really is supposed to be low and it shouldn't have been increased, then maybe the story would be different. So that's one of the things that the modelers should be concerned about, because there are some of these rate constant uncertainties in there that may have subtle effects, but they may not be so subtle. One of the problems, this is a model performance of simulating there's a large database of surrogate runs done at fairly low, closer to ambient concentrations in the new chamber. And you've seen this plot before, actually, or at least most of you have. What you see for the black dots, looking just at the SAPRC-99 now, which is the black dots, but you see if you look at the model error as a function of the hydrocarbon and NOx ratio for these experiments, which were done in a wide variety of hydrocarbon and NOx conditions, you see that there's a definite trend in the model error. The model consistently underpredicts the reactivity at low hydrocarbon and NOx ratios and goes towards performing better, and then even going towards overpredicting at the higher hydrocarbon and NOx ratios. You see this trend in the full surrogate run. So the full surrogate means it had one type of, it had aromatics and olefins and whatnot, so it had different types of compounds. With the black light source, you got the same result. But the interesting thing, when you took the aromatics out of it and did the matrix of experiments, you didn't see this trend in the model error of the hydrocarbon NOx, suggesting that this might be something due to some problem. It doesn't prove it, but it suggests very strongly that this might be due to some problem with the aromatics mechanism. But of course, now supposedly we have a better aromatics mechanism in the new mechanism, so it should fix the problem. Well, it didn't fix the problem. Matter of fact, it might have even made it a little worse. The red is the new mechanism, and basically you're seeing the same sort of model errors, and in fact the performance for the non-aromatic surrogate is a little worse. So in this regard, but basically this problem hasn't been solved with this mechanism. And I should note also, I didn't show it here, but the carbon bond mechanism is much worse as far as this is concerned. So here's a problem that hasn't been solved. Okay, so that's the summary of the evaluation against the chamber data. Then the next step in the process is to do the lump mechanism for the Airshed models, which you also have to do in order to do the base case for the reactivity calculations. And this is basically the fixed parameter mechanism that's used in the actual Airshed models, the grid models, that the ARB and other people use. And so this fixed parameter version of this mechanism was derived basically using the same lumping approaches and model species as we used for SAPRC-99. And again, as with SAPRC-99, the parameters for the species is based on that same base ROG mixture, which is a mixture based on ambient measurements in the mid-1980s. This mixture probably needs to be updated, but unfortunately we didn't get this information. We still don't have a better mixture, so we have to use the old one. Part of adapting it for Airshed models is to do emission assignments, and those were updated for this and added to the speciation database. There had to be some changes in the emission assignments because the model species in this version of the mechanism were not exactly the same as SAPRC-99. Most of them were, but what I ended up doing was representing benzene and acetylene explicitly rather than lumping them, because what I found was those, even though they're not that important for ozone formation, they're of interest for their own right. benzene because it's toxic and acetylene because it's a sort of a good tracer for vehicle emissions. But also they just do not lump well with the other species in there. Their mechanisms are unique enough that they just don't. I mean, benzene used to be lumped with toluene, but it's a lot less reactive than toluene. And then we had to use some sort of hokey emission weighting scheme, which I didn't like. Acetylene doesn't look at all. It has about the same rate constant as ethane, and so it's been lumped with that, but its mechanism is totally different, so that didn't fit either. So I decided, hell with it, I'll just make them separate. And so that requires that the emissions be done. And some of the organic acids are more explicit as well. So anyway, this mechanism was used as the base case in reactivity calculations, and this would be what would be implemented in the Airshed models when they get around to implementing it. Okay, now calculation of updated reactivity scales. This mechanism was used, and the new, new mechanisms for the individual VOCs was used to calculate new MIR and other reactivity scales that are presented to the ARB. Now, the scenarios and the method and the calculation methodology was exactly the same as used for the previous reactivity scales. So when you see the comparison of the reactivity scales, it's due only to the change in the mechanism and not to the reactivity calculation approach. Now, probably the methodology and scenarios need to be updated, but that was beyond the scope of this project. And the reactivities were calculated for a total of for over almost 1,100 types of VOCs, including those that are represented explicitly and those represented by lump molecule methods, and also a number of complex mixtures that we've calculated reactivities before. And incidentally, at the request of the ACC, we've added some unspeciated alkane mixtures, so you can use those as well. So this includes almost 300 types of VOCs that were not in the previous reactivity scales. But one class of VOCs that were actually deleted was the amines. So in the draft report, I had estimated reactivities for amines, but then we have another project with the ARB to study the reactivities of some consumer product compounds, including amines, and we found that the mechanisms didn't work at all, and so what I had there before was wrong, so I had to be deleted. But for this other project, we'll be doing an updated scale, and those of you who are interested in that, I'll be discussing that this afternoon. Before I go into the actual reactivity calculations, it might be of interest to see what the effect of the mechanism updates on the actual maximum ozone is. Now, the real test will be when you put it in a real Airshed model for Los Angeles or whatever and calculate it, and that hasn't been done yet. But you get some idea, at least of the trends of what it looks like in the box model calculations, like done in the ECMA scenarios. At least it'll give you the directional trend. And what you see, what this shows is the change in the maximum ozone, SAPRC-07 compared to SAPRC-99, in the base case scenarios used in the reactivity calculations. The blue dots are the base case scales where basically the NOx is not adjusted. And so these are actual comparison of the mechanisms for the same scenarios. But for the MIR, MOIR, and EBIR scenarios, the methodology for deriving them involves adjusting the NOx in order to get MIR, or maximum ozone, or eco-benefit conditions. And so what that means is if you change the mechanism, the NOx that gives the MIR conditions, for example, is slightly different for one mechanism than the other. So in some respects, if you're comparing the MIRs, they change comparable to the base case, but there's not exactly the same NOx. But it's the same type of chemical conditions, so you're getting the comparable effect. And generally, I'll show you what happens in the same NOx in a minute. But generally, what the updated mechanism caused about an average of a 5% decrease in ozone in these box model calculations. And I suspect it's primarily because of the OH plus NO2 rate constant. But maybe I'm wrong. But it is a less reactive mechanism, so it'll go more towards the carbon bond mechanisms. And the modelers may not like that, but that's the way it came out. Now, if you do, this scale shows when in the previous one, the MIR, EBIR, and MOIR scales had the NOx adjusted individually for the chemical mechanisms, so they were different. But if you do the calculation where the MIR, et cetera, NOx is exactly the same as in the SAPRC-99 scale. So basically now you're comparing scenarios that are exactly the same emissions. You get a much larger effect for some of them, and also you get a more regular effect of a definite a case of the discrepancy between the mechanism getting greater as you decrease the ROG to NOx ratio, which is, in some extent, mechanisms are more sensitive at the low NOx ratio, so you expect if it was different, it'll be more different at those conditions than at the high NOx conditions. And in fact, with the MIR scenarios, which are probably the most sensitive type of scenario that you have, you get almost a 30% change in some cases. So this is a very large, sort of surprisingly large change. Now, we would have to, the base case is the same as in the previous one because the NOx wasn't adjusted. So it'll be interesting to see what happens when you use an actual Airshed model. I doubt you'd see anything like 30% changes, but you will probably see less ozone. Now, as far as the reactivity, this is the changes in the MIR values for all the VOCs that are present in both of the 2002 scale and the new scale. And this line here is the one-to-one line, so anything that falls on this line didn't change. And you see that, and the other lines is plus or minus 30%. So you see that most of them didn't change by more than 30%, but there were a few outliers. On the average, the MIR went down by about 10% on the average, and the absolute value of the change is, the average of the absolute value is about 15%. So on the average, that was about the change. But of course, the regulatory point of view, the most important thing is the relative reactivity. These are the compounds that had the largest MIR change. The largest of these was 3-methoxy-1-butanol, but that wasn't because of updating the mechanism. It's because you have a question.
Remember in the last slide, you had, I think, 5 or 6 outliers. Do you happen to remember what any of those are?
Well, these are some of them. And then the other ones might be compounds that are similar. But I sort of sorted the differences, and this is what came up. The 3-methoxy-1-butanol, it wasn't a matter of updating as much as having to review everything, and then suddenly, oh, geez, the rate constant is off by a factor of 10. So this was actually correcting an error here. So any fans of this compound are sort of out of luck in this case. But now the chlorinated compounds, the reactivities went up because, as I mentioned before, the halogenated substitute oxygenated products seem to be much more photoreactive than the unhalogenated ones. So they added a separate model species for chloroacetaldehyde and a separate model species for chloroacetone, which is more photoreactive, and then used those for these chlorinated compounds, and so that increased their MIRs. Some other compounds, the indene changed because I decided it was probably a less bad approximation to represent it by styrene than by tetralin. They're probably both bad approximations, but that seemed like a less bad approximation, but that resulted in a decrease. The furan, I actually derived an explicit mechanism as a process of trying to do explicit mechanisms for the other aromatics. It was previously represented by xylene, but that change is probably within the big uncertainty of those estimates anyway. So these are some examples of VOCs that changed. Most of them didn't change that much. Okay, so now to go into the, guess I'm better wind up pretty soon. Okay, to get into the remaining work that needs to be done, well, it's sort of the near-term work that needs to be done is that this mechanism needs to be implemented in the full Airshed models. I'm working on, I had developed files for implementing it in the Models 3 system or a CMAQ system, and I need to prepare these files. Perhaps a more important problem is the peroxy radical operator method involves some use of some steady state approximations that some of the software used in some of these models doesn't handle. So we'll have to either use a less computationally efficient method to represent these reactions, or somebody's going to have to get in and reprogram some of those chemical mechanism implementing programs. But so there's a little bit of work here, although they need to improve those chemical mechanism implementing programs anyway. Maybe this will force them to do it, but I doubt it. Anyway, okay, and then as I mentioned before, we need to develop new mechanisms for amines. The chamber data indicate that amine mechanisms are wrong, but we are in the process of doing that, and we have new chamber data, and we're analyzing it, and hopefully by the end of September I'll have an amended scale that has the amines added back in. And their reactivities will definitely be a lot lower than the upper limit reactivities in the previous scale. In fact, some of them will be negative, probably. One of the tasks of the project, which we didn't succeed in at all, but what some of the modelists were interested in, was developing a condensed version of the mechanism that might be comparable in efficiency to carbon bond 4. That needs to be done, although somebody needs to find the money to do it. It's not a huge amount of money, though. And the other thing that the ARB wants to do, which I think is a good idea, and they did that for SAPRC-99 as well, is to have a comprehensive peer review of the mechanism and see if there are any mistakes and whatnot. And in fact, in the process of preparing this presentation, for preparing one of the slides, which I ended up not showing, but I found that there was actually an error in the peroxy radical implementation of the thing, so I had to go and recalculate everything. It didn't affect the ozone reactivity, but what I should have done was just not corrected the error and see if the peer reviewer noticed it. Okay, now the recommended research, one of the things that I think that should be done sort of maybe in the next year or so, maybe is in the process of evaluating, the reasons for the model performance and problems in simulating the chamber data really need to be elucidated, because I think some of these problems may be due to bad chamber data, but I think when you're having this large and varied data set and you're seeing these consistent trends, I think a lot of these problems are due to some subtle problems in the mechanisms that we don't understand, like maybe the interplay between the OH plus NO2, maybe the pan chemistry, maybe something else. But why do current mechanisms underpredict ozone and surrogate experiments at low RG to NOx? Well, we think maybe it's the aromatic mechanism just by looking at the different kinds of experiments, but what is it about the aromatics mechanism that caused that, or is it in fact something else? And if you change the OH plus NO2 mechanism, rate constant, it will change. But why did the mechanism updates cause fits to the chamber data to be worse for some types of mixture experiments? It's not a whole lot worse. It's statistical significance. Maybe a statistician wouldn't say it's that significant, but it seems significant to me and indicative that something in the process of change wasn't quite right. And what's the implication of these discrepancies in the simulation of ambient conditions, and for that matter, simulations of control strategies? And what uncertain rate constants or other parameters affect these performance issues? And once you sort of get the answers to some of these questions, then you could sort of direct the research needed to address these issues. Like when the carbon bond mechanism was first developed, it had sort of a screwy way of representing a pan chemistry, and they did sensitivity studies to realize that that was causing mechanism differences, but it was fairly easy to address by doing focused research. So maybe we could focus on what the particular problem is and just do some basic studies at it. We may be able to get at some of these. So I think in order to do that, certainly the tools of uncertainty analysis and process analysis which have been developed could be useful and should be applied for that, maybe in the context of the chamber simulations. But I think new analysis methods and approaches would be useful, some creativity there to try to get at the bottom of some of these problems. And that's not just an academic exercise for trying to understand how these things work, but to understand what needs to be fixed and whether what needs to be fixed is significant or not as far as the predictions that you all are interested in. Now for aromatics, although the updated mechanism is more chemically reasonable, it's still simplified and it still has some of the performance problems. Maybe some of them aren't quite as bad, but they're still not good enough. As part of this project, I attempted to develop explicit mechanisms for the aromatics that could predict reactivity differences among the isomers, but that wasn't entirely successful, and I finally had to give up on that approach. And now, but actually to develop, I think more than just small chamber experiments and chemical mechanism work is needed. What's really needed to develop improved aromatic mechanisms is breakthroughs in measurement methods to try to identify and quantify reliably all the products that are formed, and also breakthroughs in theories in order to try to better calculate or estimate what the reactions of these types of intermediates can be. And I think work is needed in that area. And it may be somewhat longer term, it may not be, but it certainly should. If you're really interested in getting a breakthrough in the aromatics, I think that's what's going to be needed. In the meantime, a systematic study, examination of effective alternative aromatics representations may be useful, but these alternative representations are still limited by what our imagination is about what these things are. Unless we get some breakthroughs in theories or data, we may be too limited in what the possibilities are and overlooking something that might be what it really is. As far as the mechanism generation system may be sort of hypothetical and theoretical to a lot of you, but it's actually critical to the reactivity scale for many of the VOCs that are there. A large number of the VOCs, especially these glycols and glycol ethers and all these strain combinations that end up being stationary source people really like using for different reasons. There's too many of them really to study experimentally, and the reactivity estimates for them is based on the estimates of the system. And it actually doesn't perform that badly, but it should be updated as well as the rate constants in the base mechanism. And we updated some of them, but not all of the many estimates are involved, so this needs to be updated as well. And there's sort of gaps in our ability to estimate many types of reactions, particularly halogenated reactions, and also unsaturated compounds that would improve it. And I think this sort of goes on to the next thing, but as far as adapting for SOA prediction, it should be methods of estimating volatility should be implemented into that to include which of these products that is predicting the form are going to be really volatile enough to react, or maybe they won't be. And even if all you're interested in ozone, that may affect things. Finally, well, the mechanism generation system needs to be documented in the peer-reviewed literature and in its estimation method. And that, of course, is my deficiency, but I need to really do that. And the other thing is the European master chemical mechanism is really the closest competition or alternative that exists to the SAPRC mechanism right now. And there's a major, and it's actually fairly well supported, and there's very active and creative work being done there. And it's another comprehensive mechanism that's based essentially on estimation methods. And I think it would be beneficial to compare them, and probably we could learn from each other as far as getting both of them better. Although it doesn't mean that the world would necessarily be the better if they were the same, because having two alternatives is also good, but I think comparison would be good. As far as adaptation to SOA predictions, although this project was funded mainly from the point of view of ozone and not from the point of view of SOA formation. The SOA research, mechanism research, seems to be sort of done in a different compartment or something. But I think as far as the scientific basis, adapting a single mechanism, whether it's SAPRC-07 or whatever, for both PM and also ozone and gas phase predictions would be a more integrated approach. Because in order to do secondary organic aerosol correctly, you have to do the gas phase correctly. So, and since you're concerned about getting the gas phase right in the ozone modeling, and you want to need the chemical detail for the ozone reactivity, why not also use that chemical detail for better PM, the secondary PM predictions? And this would require, and the present mechanism, SAPRC mechanism really isn't suitable for that now, because you have to add organic model species that represent low volatility SOA products. And in order to actually utilize the interface between the mechanism generation system and the actual mechanism in the model, you need the mechanism generation system to support this as well and incorporate estimates of volatility in it. There is theory of estimating volatility now that could be done in that. And then the other important part is that the ozone mechanism is built upon this large body of environmental chamber data, and that's really where it gets its validity from, to the extent that it has validity. The PM mechanisms, which in the chemistry, the PM is a lot more complicated and has a lot more uncertainties. And it's even more important that be evaluated against well-characterized chamber experiments. And perhaps it's also even more important that it be done at ambient concentration levels, because the concentration level is probably even more important in the case of PM than it is in the case of gas phase things. And the funding for the chamber research of this type is very limited at the moment. And that leads into the recommended chamber database. And so at this point, maybe I should try to do an advertisement that I think they need to take advantages of the capability of the UCR-EPA chamber that was developed for doing lower concentration work and utilizing it for PM and secondary organic aerosol mechanism evaluation. This allows for well-characterized experiments at ambient levels, which is difficult in other chambers. And the other thing you should be aware of is that researchers at CE-CERT were successful in getting a KEC grant for several $1 million to obtain several $1 million worth of advanced PM characterization equipment. So we're going to have all this great equipment, and the problem is that the funding level for this chamber is sort of running low, and David Cocker, who's sort of the PM person there at the chamber, is very good at getting NSF grants to support his graduate students to do things. But what it doesn't study is for the technicians that actually keep the chamber running and the instruments repaired and whatnot. And now we don't have money to pay the technician to do that. And so we might be able to get him onto other projects, but we're getting to a point now that if we lose some of these people, we're going to lose a knowledge base that you may not get back. And this has been supported for a lot of years by my work in this gas phase stuff, and there might be some additional work coming on that, but not as much. And I'm basically semi-retired now, and the one thing I've definitely retired from is begging for money. But so now what I'm doing here is begging for money, but it's not it's not for me. And I think you need to be aware of this problem where you're going to lose this capability, but only if you see that there isn't. I think there's a real need for the better PM chamber data, and this is one way to do it. And on the other area, there is methods that are needed to improve the sensitivity of chamber experiments to effects of oxidation products on reactivity. I had discussed this before, and there was a research concept that wasn't funded this year, but it might be funded next year. The chamber data is still not adequate for evaluating predictions of temperature effects on pollutant formations. We're capable of doing that. The data is very limited in that regard. The mechanisms are still highly uncertain for many types of compounds, or at least for some types of compounds, particularly amines and some other. So there will probably always be a need for some experiments for particular compounds that are of interest. And finally, this is the last slide, recommended research for updated reactivity scales independent of the chemical mechanism. I think the Reactivity Research Working Group has worked for a number of years on the problem of improving methods. Well, first seeing what's the best, whether reactivity really is a scientifically valid way of doing things. And I think they sort of concluded that it was. But what really the next step was is how's the best way to do it. And one of the conclusions was, I think, sort of the MIR, it isn't all that bad. It may be good enough, but it's probably not the absolute best scientifically that could be done as far as the optimum way of assessing reactivity for a national reactivity scale. And I think that California should continue to use a national reactivity scale, because if you start looking at local reactivity scales, you can get a situation where the reactivity scale today in Los Angeles is going to be different than the reactivity scale tomorrow. And the reactivity scale in the Central Valley is going to be different than Los Angeles or other non-attainment areas. But when you look at all the distribution of conditions, they'll be different enough that you might as well use the national scale anyway. And since California is the only ones that's funding it, the rest of the country will use it in any case. But the problem is that the MIR may be good enough now, but the scenarios used are way out of date and need to be updated. And this isn't big money to update at least these ECMA scenarios, because right now they just represent much higher pollutant levels than current situation. Like the Los Angeles scenario gives a maximum ozone of 500 ppb. And the last time I looked, Los Angeles didn't have that much ozone. But now methods exist and have been developed for deriving box model scenarios from these grid model calculations that you actually use in your attainment demonstrations. So you could actually use if it's not practical to develop reactivity scales from grid models, which it might be practical, but if it isn't, you could develop at least a number of box models that have a regulatory pedigree that you could, that would be, and a scientific pedigree that you could use. And the base RG mixture also needs to be updated when that is needed for the LEP mechanism as well. The one thing, in any case, you're doing a good job in funding the best chemistry that goes into the reactivity scales, but if you don't, if you just think that the old scenarios are good enough, eventually it's going to cause, they're going to get more and more out of date, and it'll cause a loss of credibility in the reactivity program. So I would start thinking about that part of it as well. Okay, that concludes my presentation.
We have some time for questions. And well, actually, I have a question from Doug Lawson, National Renewable Energy Laboratory. With oxygen in gasoline and now in the diesel fuel, what additional work needs to be done to update the mechanisms? Certainly, additional analytical work needs to be done to properly identify all of the oxygenated compounds that would be produced by normal and high emitters from the mechanism.
Well, it depends on what compounds they find. If it's the compounds that have been reasonably well characterized as far as the mechanism, there may not be much mechanism work involved. The work would be the analytical work that he had discussed. If something turns out to be really important and there's no chamber data to support the mechanism, then maybe that should be looked at. I suspect that it'll probably not yield a whole lot of mechanism work that's needed, but until I see the actual data, it's hard to tell. The other thing is a lot of these oxygenates, if they just have oxygens and hydrogens and carbons and not double bonds, the mechanism generation system doesn't do that bad a job for them. And unless they really dominate in the mixture, the uncertainties involved in that is probably not large enough for the vehicle people to be concerned with compared to some of the other uncertainties that they have. But it depends on the but if they get some sort of weird compounds in there, then that's a different story. Now, if you see something in there that's not in the reactivity tabulation, that's when you can give me a call.
Okay, any questions for Okay, I have second question from, again, Doc Larson. The current ambient 6 to 9 AM VOC NOx ratios in the South Coast are around 4, which coincides with the maximum discrepancy or decrease in ozone formation as compared with SAPRC-99 as you displayed in one of your graphs. What are the implications of this decrease in ozone formation at the current and the low VOC NOx ratio?
Well, I'm not exactly sure what you mean by the implication. I guess he's referring to the plots to this. Well, the implication is the model doesn't really, well, first the model is more sensitive to differences in the mechanisms at the low hydrocarbon and NOx ratios. And therefore, any uncertainties in the models are sort of magnified under those conditions. And the chamber data suggests that they tend to underpredict ozone under those conditions, which means that they tend to underpredict the rate that ozone is formed. As you have the source area where the NOx and the hydrocarbons are emitted, and generally the hydrocarbon and NOx ratios are the lowest then, and then the ozone gets formed as it moves along and the ratio gets higher. And so what the model can predict, the ozone is formed slower than might be really happening. Of course, when that happens, trouble with the ambient air, when that happens, you say, well, maybe the mechanism is wrong, but maybe the emissions are wrong too, and probably the emissions might be more, the emission uncertainty might be more important than the mechanism uncertainty. So it's sort of hard to break it down so that what you would like is a mechanism that you could have confidence in its predictions under those conditions. So then if they disagree, then you can say, well, maybe it really is emissions. But right now, there's always sort of a, you don't really know where you are. So what the implications is that you need to try to understand what the cause of this discrepancy is, and then see what its implications in the Airshed calculations are.
Yeah. Regarding the chlorine reactions, I wonder if you compare the uncertainty with our classical VOCs plus OH reactions and versus the VOC plus chlorine reactions. How different is your chlorine reactions more uncertain than the OH reactions, or how adequate is the database that you have?
So you're asking whether the VOC plus chlorine reactions are more uncertain than the VOC?
Yeah.
I think in the case of the alkanes, they're probably comparable. In the case of the olefins, they're probably a lot more uncertain as far as the mechanism. I think the importance, unless you're looking at some sort of weird atmosphere that's right downwind of a chlorine plant or something, it probably isn't going to be that important as far as what the VOC plus individual the individual chlorine reactions are. Most of the chlorine that's emitted that reacts with VOCs will react with the alkanes because there's more alkanes there and it has very high rate constants of alkane. Unlike OH, which reacts slower with alkanes than other things, than olefins and whatnot, chloride sort of reacts with high rate constants of practically everything. So it's mostly the alkanes that they'll react with, and as far as the impact on the model, I don't think that'll be a big factor. If you have chlorine there, you should represent the fact that the chlorine is there because it'll impact the radical levels. But as far as what it does when it reacts with the VOCs, I don't think that'll be a big uncertainty in the mechanism, as long as you have it in the mechanism.
Thank you.
Well, you mentioned the chlorine chemistry. How important is the chlorine chemistry to your overall mechanism?
Well, it depends on what the chlorine emissions are. If you're doing in the reactivity scales, it's not important at all unless you have a chlorine-containing compound. And then if you're doing a chlorine-containing compound, well, one, it allows you to do it if it's if for some of them that generate chlorine, you need to have the chlorine chemistry in there. So otherwise, you wouldn't be able to do the reactivity, because the SAPRC-99 reactivity scale really didn't have chlorine-containing compounds, or it used sort of very crude parameterized mechanisms for them. So the mechanisms for the chlorine-containing compounds now are a lot less, are better. But as far as the actual base case or the ambient modeling case, that just depends on what the chlorine emissions are.
Any more questions from the audience? If not, let's thank our speaker, Dr. Carter, again. Thank you very much.